Our ability to convert natural resources to usable forms of energy has always been necessary for growth and advancement. The discovery of cheap and seemingly endless energy in the form of coal and oil have allowed for this progress to increase exponentially since the first industrial revolution. Now it is clear that these resources are in fact both limited in quantity as well as detrimental to our environment. We now face a modern crisis of energy. How do we continue on this trajectory without fuel? If we step back and observe, it seems that free energy is everywhere. The sun in the sky, a swift breeze, and plants somehow surviving in the concrete jungle. Maybe it's not that we are facing an energy crisis, but a conversion crisis.
To address this global crisis, scientists and engineers alike have been formulating ways to reduce our reliance on traditional energy materials like coal and oil. Solar, wind, geothermal, and the uses of biomass as fuels are all strategies to more sustainably supply energy to all who demand it. But this push towards renewable and alternative energy resources in recent decades has been met with some resistance due to limited availability and high startup costs. Solar panels in particular have a very high initial startup cost, and although over time the energy produced will eventually pay for these costs, this buyback period takes several years. While these renewable energies could become more cost efficient through advances in modern technology, it will not address the growing demand for mobile fuels for transport. Even the best electric cars still require gasoline for ignition and some fuel input while driving.
As oil reserves continue to be depleted, the necessity for transportable fuels will continue to increase. Biofuel production through the extraction of oil from biological sources provides a promising solution to these energetic demands. Where we fall short is efficiently converting the sun's radiation directly into usable energy. We are surrounded by an endless number of photosynthesizing plants which perform this task seamlessly. Buried fossilized biological matter from millennia past have provided us with the reserves of petroleum that we have today. Could we not then turn back to these plants for the fuels we so desperately need today?
Corn ethanol, more commonly known as E85, represents the most active work for the production of biofuel today. However, as with many potential sources of biomass, the use of corn for gasoline has been criticized for taking away from an already stressed food industry. In addition, the production of many biofuel products is much more expensive than petroleum extraction, while at the same time yielding fuels which are lower in energy potential. Microalgae have been proposed as a model organism for use in the biofuel industry due to its high lipid content, nutrient tolerance, and rapid growth rate. Algae are generally non-motile, single-celled organisms existing in a variety of aquatic and terrestrial environments. Their size and reproductive qualities make it possible to grow algae in dense aquacultures, eliminating the need for large acreages for cultivation of vascular plants such as corn. Sustainable systems of algae cultivation have also been studied in conjunction with wastewater treatment due to the ability of these organisms to survive under a wide variety of nutrient conditions. Through our research into renewable fuels in Colorado, we came across two organizations heavily invested in the production of biofuel. The first was the National Renewable Energy Laboratory, which conducts research into several different avenues for renewable fuel production. We talked to Maria Girardi from NREL about their renewable fuel efforts and the use of algae as a food stock for the production of biofuel.
So NREL, as a laboratory, has researched in a number of different technologies, renewable energy technologies, such as solar, such as wind energy, such as biomass by itself for conversion into ethanol. Use algae that are known to over-accumulate lipids, such as chlorella or nanochloropsis or Sanidesmus. And they do the whole process. They start with the cultivation, issues related to cultivation, all the way to lipid extraction and lipid quantification. There is a group that actually studies the conversion of that particular lipid into biodiesel. We don't do much besides that. We have collaborations with industry or other research laboratories to complement the work that we do here.
While the use of algae for biofuel production seems promising, as with any alternative energy, it is important to address the economic viability of this process on a large scale. Blue Sun Biodiesel represents a company picking up where research groups like NREL leave off, trying to commercialize the growing industry of biofuel. While they don't work directly with any production of algal biofuel, this company is one of the largest producers of pure biodiesel product in the U.S. We talked to Steve Bond from Blue Sun about the current status of alternative fuel production. At Blue Sun, they utilize a variety of different vegetable oils and through a chemical process called transesterification, convert these oils to 100% pure biodiesel. This simple reaction converts triglycerides, or oil, and ethanol to diesel and glycerol. The diesel product is then sold wholesale to fuel distributors who typically mix the pure product into usable blends with petroleum diesel, the most commercially available of these being the B20 blend. At present, most of the oil used in this industry is virgin oil, or oil extracted directly from plants. So what is the status and future of algae to replace these feedstocks?
Right now, we do have the tools, and there are a lot of groups, a lot of research groups, as well as companies involved in trying to make this process commercial. And when NREL did a techno-economic analysis of algal biofuel production, there were three important results. The first one is that we're not there yet. The amount of lipids produced by algae at the moment is not high enough to result in diesel at a reasonable cost, a competitive cost with gasoline. Second conclusion, they compare two different methods of cultivation. They compare open pods with photobioreactors. And the conclusion that they came to was that right now, photobioreactors are extremely expensive, and they increase the cost of the diesel produced by the process, way above that of using open pods. There is a lot of need for financial support of this research, so we're not there. There has been a lot of financial support from the Department of Energy to companies and to individual researchers, but there's a lot of work that needs to be done before this becomes a commercial process, basically.
While at NREL, algae biofuel still has not progressed to the point where biodiesel can be produced at a competitive price to petroleum. At Blue Sun, it is a different story. At their facilities, the production cost of pure biodiesel is about $4.55 per gallon, compared to the price at the pump for petroleum diesel, which is about $3.20 per gallon. However, the actual cost of biodiesel decreases before reaching consumers due to various credits and subsidies. The federal blender's credit reduces the cost by $1, and 1.5 REN, or renewable fuel credits worth 70 cents each, can reduce the price at the pump to about $2.75 per gallon. According to Blue Sun, this difference is necessary to incentivize consumers to choose biodiesel over petroleum. So if biodiesel production through traditional methods has already reached a point of economic viability, what need is there for continued research into using algae? We questioned NREL on the benefit of algae cultivation in comparison to traditional food stocks such as corn and soy.
The main difference is that the algae occupy or can produce biofuel much more efficiently than plants. So you need less of a surface area to produce the same amount of biofuels as plants. Algae, depending on the algal strain that you choose, do not need pure water or clean water. You can grow algae in wastewater, for instance. So that eliminates a lot of the problems that one has with growing crop plants or displacing crop plants to produce biofuels instead of food. That's the famous food versus fuel controversy. Algae do not need cropland. You can grow algae in the ocean depending on the type of alga that you're using. So you can have certain areas of the ocean devoted to growing algae for biofuel production. You're not displacing cropland to do that.
Whether our mobile fuels in the coming decades originate from the Middle East, cornfields, or algal ponds, it is clear that our current reserves of petroleum will not last indefinitely. In fact, many believe that we are already experiencing a terminal decrease in oil extraction. Although the development of biofuel from microalgae is still far from being sustainable economically, it does demonstrate a promising pathway for sustainable fuel technology in the future. The answer to our energy and environmental crisis is not going to be solved by one energy source. There will have to be many different forms of alternatives and renewables implemented, working together to achieve a more sustainable and an environmentally friendly way of obtaining energy. The limited supply of oil is definitely a driving factor for research and development, as well as the establishment of alternative energies. But is this enough? Scientists have concluded that our environment will be degraded on a detrimental scale well before we have used all of the oil and coal reserves. So how then do we promote the use and generate funding for alternative energies? Passing legislation requiring a certain percentage of vehicles to have fuel flex capabilities would be a huge step for biofuels, including algae. What lies in the future of alternatives is in the hands of both the people and the government. Our current energy crisis can and will be solved if our country invests the time and money needed to improve and expand renewable energies.